Hey everyone, and welcome back to another Explainer. Today we are diving straight into the completely invisible world of chemical engineering to see exactly how scientists solve microscopic traffic jams. When a normal factory floor gets backed up, you can just look down from a catwalk and pretty easily see where the conveyor belt is stuck. But how do you fix a bottleneck that is literally millions of times smaller than a single grain of sand? Well, that is the absolute thrilling challenge of chemical reaction kinetics.
So, let's really think about this fascinating question. I like to picture chemical engineers as molecular detectives trying to optimize a totally invisible factory. They obviously can't see the individual molecules reacting with their own eyes, but they can measure the macro effects. Things like sudden temperature changes, pressure shifts, and just how fast raw materials are churning into finished products. Their ultimate goal? To pinpoint the single slowest step in this invisible factory and speed it up. And honestly, it requires some incredibly clever scientific sleuthing.
Because remember, these reactions are happening at a mind-bogglingly tiny scale. Molecules are undergoing these fleeting transition states where they are literally twisting, slamming into each other, and rebonding in absolute fractions of a second. The sheer complexity of it all is just staggering when you really think about it. So our job today is to figure out exactly what slows this rapid, chaotic, microscopic process down.
All right, let's kick off our investigation with Act 1, the invisible assembly line. Because before these chaotic gas molecules can react efficiently, we actually have to tame them by anchoring them down to a two-dimensional catalyst surface.
Now, there is a massive difference in how molecules actually stick to these surfaces. We're looking at two main players here, physico-sorption and chemisorption. Physico-sorption just relies on weak van der Waals forces, with an energy change of only negative 0.5 to 5 kilocalories per mole. It's basically the molecular equivalent of static cling, super weak. But chemisorption? That creates strong, actual chemical bonds at highly specific active sites on the catalyst.
To put that difference into perspective, chemisorption requires 10 to 100 kilocalories per mole. I mean, that is a massive jump. That perfectly matches the energy of actual chemical reactions. So we aren't just talking about molecules casually resting on a surface. No, they are chemically locked into precise positions and orientations, completely primed and ready for the next step of our assembly line.
Which brings us to Act 2, finding the bottleneck. Now that our molecules are securely anchored, we need to find the holdup. Because just like a real-world factory, a chemical process is literally only as fast as its slowest worker. And in chemical engineering, we call this critical worker the rate-determining step.
But actually, before we even look at catalyst surfaces, let's look at a slightly simpler scenario, pure gas pressure. The Lindemann theory shows us just how tricky these molecules can be. For a molecule to react on its own, it has to get through 3 steps. Step 1 is activation. It acquires energy by colliding with another molecule. Gets hyped up, right? But step 2 is deactivation. It might just collide again and lose all that energy before it even has a chance to do anything. It's only in step 3 that the actual reaction finally happens, and it transforms into a product.
So check this out. Just changing the pressure completely shifts the reaction's mathematical order, simply by altering how often these molecules bump into each other. At high pressure, it's totally crowded. Collisions are so frequent that deactivation is incredibly fast, so it acts as first order. At low pressure, it's a ghost town. There are so few collisions that activation becomes the slow step, making it second order. And right in the middle? At intermediate pressure, we get this crazy tug-of-war that gives us bizarre fractional observed orders like 1.3 or 1.75. That fractional order is basically a giant neon sign telling us the reaction is caught directly between competing controls. Okay, returning to our catalyst surface. We use something called Langmuir-Hinchelwood kinetics to interrogate the whole process. Our primary suspects for the bottleneck usually fall into 3 specific categories. First, adsorption control. Is the whole system lagging because molecules take too long to bind to the active sites? Second, surface reaction control. Is the actual chemical transformation between the anchored species the slow part? Or third, desorption control. Is the release of the newly formed products holding everything up? Now, that last one, desorption control, it is incredibly stubborn. When products flat out refuse to leave, they essentially poison the surface. It's a huge roadblock. This actually leads to negative reaction orders, meaning adding more reactant literally slows things down, and zero pressure dependence. It is the ultimate microscopic traffic jam. It's feedback inhibition entirely clogging up our invisible assembly line simply because the finished goods will not get off the conveyor belt.
But wait, what if the chemistry itself is actually lightning fast? Welcome to Act 3, Traffic Jams in Catalyst. Sometimes the chemical reaction isn't the problem at all. Instead, the molecules are getting lost before they even reach the active site. Let's explore the physical, microscopic mazes where these physical traffic jams happen.
Just imagine a reactant molecule trying to navigate a wildly complex, twisted tunnel system inside a solid catalyst pellet. We measure this physical maze using a metric called effective diffusivity. You calculate it by taking the pore's void volume, its porosity, and dividing it by the tortuosity. And tortuosity is exactly what it sounds like, the zigzag, winding path length that molecules must physically travel. This means the effective speed of our reactants is drastically slashed simply by the twisted geometry of this microscopic maze.
And depending on the size of the tunnel, molecules face totally different physical obstacles. We classify this as bulk diffusivity versus Knudsen diffusivity. Bulk diffusivity dominates in larger pores, anything bigger than 1 micrometer. Here, molecules are mostly just bumping into each other in wide open spaces. But Knudsen diffusivity, that takes over in incredibly small pores, like between 10 and 1,000 angstroms. Here, the space is so insanely tight that molecules are constantly ricocheting off the walls like tiny pinballs, rather than bumping into one another.
So, chemistry can be the bottleneck, or physical transport can be the bottleneck. How do we figure out which one is the actual culprit? Let's turn to Act 4, the engineering toolkit. How do engineers accurately diagnose these invisible problems? Well, by using some really clever macro-scale physical tests to expose those microscopic flaws.
By physically messing with the environment, engineers can successfully isolate the bottleneck. If they spin a liquid reactor faster and the reaction suddenly speeds up, they know for a fact the bottleneck was molecules struggling to push through the liquid film surrounding the catalyst. If they pump fluid harder and things change, boom, it's an external mass transfer limit. And, this is my favorite one, if they literally crush the catalyst into fine dust and the reaction suddenly spikes, they've definitively proven that the internal physical maze, that pore diffusion we talked about, was causing the traffic jam.
And, the math itself actually provides a smoking gun for the detectives here. Engineers look at something called the apparent activation energy. If the experimentally measured energy required to make the reaction happen drops to exactly half of its true chemical value, it is a mathematical guarantee that the reaction is being choked by internal pore diffusion. No guesswork needed. The numbers literally point right to the maze.
Now, to double-check their physical tests, engineers use complex mathematical models known as dimensionless criteria. The Weiss-Prater criterion mathematically evaluates the internal diffusion limits. Basically, if the value is less than 1, the inner maze is totally clear. Meanwhile, the Mears criterion assesses the external mass transfer limits across the stagnant fluid film on the outside of the particle. Together, these tools mathematically guarantee that physical transport issues aren't secretly biasing their chemical data. It's brilliant.
So, as we wrap up this explainer, we've seen how scientists hunt down the invisible bottlenecks that limit progress at the microscopic level. Whether it's a tight physical maze or a stubborn chemical product is refusing to leave the assembly line, the entire system is completely at the mercy of its slowest step. So I'm going to leave you with a final thought to ponder today. If this fundamental law dictates the speed of absolutely everything in nature, what is the rate-determining step shaping your own everyday progress? Really think about it. Thanks so much for learning with us, and we'll catch you on the next explainer.